Welcome to our exploration of roller coaster physics, where we'll uncover the scientific principles behind every twist, turn, and drop. Brace yourself for a journey into the thrilling world of forces, energy, and motion. In the beginning of this roller coaster, the most prominent energy type is potential energy. As the ball is rising up the spiral lift, it can be assumed that the potential energy is gradually increasing. When the ball reaches the top of the lift, the potential energy has reached its maximum level and can be measured at 0.025 joules. This potential energy is then converted into kinetic energy as the ball begins to roll down the ramp. As the ball rolls down the first curve, the kinetic energy is then transferred into potential energy as the ball slows. This potential energy is then converted into kinetic energy when the ball begins to roll down the ramp. And so this process continues until it reaches the spiral elevator once again. Ultimately, within this roller coaster, there are two main energies, kinetic and potential energy, which can be considered interchangeable throughout the curves, ramps, and straights. This process once again repeats itself with the ball being at its highest potential energy when at the very top of the track. This potential energy is then transferred into kinetic energy as the ball rolls itself down the ramp. This process once again repeats itself until the ball reaches the second curve. The potential energy is then very high right before the ramp where it goes into the curve. This potential energy is then transformed into kinetic energy as the ball rolls down the ramp into the loop. The kinetic energy is at its highest point when at the very bottom of the loop, which is then transformed into potential energy at the very top of the loop, which is then converted into kinetic energy when the ball reaches the bottom of the loop once again. The success of this roller coaster cannot only be attributed to the energy transfers, but Newton's first law of motion, or the inertia law. He says that an object in motion must stay in motion unless acted upon by an external force, which in this case would be normal force or the weight of the ball. However, as the centripetal force outweighs the normal force, the ball is able to make its way along the track without losing contact. In order for an object or a ball to make its way around a loop, the centripetal force must be greater than the normal force or weight of the object. In this case, the centripetal force is 0.6 newtons and the weight or normal force is 0.083 newtons, meaning the ball was able to make its way along the track. As you can see here, the ball has not made its way successfully around the track, and it has lost contact. This is due to an insufficient amount of centripetal force in comparison to the normal force or weight of the ball. As you can see in my calculations, I have worked out the minimum velocity of the ball in order for it to make its way around the loop, and the minimum height in which the ramp can be leading into the loop. I have worked out that the minimum height of the ramp can be 2.5 times the radius, which would be 10 centimeters. The ramp used here was 9 centimeters, and that can be attributed to the fail. If you were wanting to make some improvements to this roller coaster design, I would consider changing the shape in which the loop is. Although it is a perfect circle, it cannot be considered the perfect loop. A perfect loop in the sense of a roller coaster would be a teardrop shape. This is because the distribution of g-forces in the way that it would feel for the person on the ride would be more even as opposed to in the loop, where the weight feels very heavy at the bottom and really light or weightless at the top. Whereas in a teardrop shape, the weight could be evenly distributed throughout the shape.